Oh my God.
Yeah.
Oh.
So how does it feel to be teaching your
The
last class? Yeah.
Oh, well, I'm absolutely delighted that it's the last one. Can't wait. I wouldn't dream of extending it for another year. I probably should have quit a year ago.
You have to show us your
My
last
grey
cup
hair?
of coffee.
Oh, your last
here's
cup
my
of-
last cup of
Oh, and
coffee.
show what it says on it. I love
And
that.
it
Youth
says,
is wasted on.
"Youth
oh,
is
I love
wasted
that.
on the young."
You have to see that.
Youth is wasted on the young.
I think we
It's
got
presumably said by somebody named
George.
George Bernard Shaw.
A
Have you
minor
heard of
figure,
him?
very
Yeah, I
minor.
think so.
Very minor.
Well, that's enough now, don't you
Okay.
think?
Sure.
Yeah.
That's
Alright.
very unlike his wife.
It's a paper, so are my fingers in the way?
No, it's fine.
Can you read it?
Yeah, I think so.
Stick this
Basically,
in a VCR.
in case those of you watching
Yes.
this were
Yes.
wondering,
Yes.
we're here on the occasion of the final day of classes for Physics 153, the last course to be taught by Professor Gerhard L. Weissler, our dad. You can switch to the other one.
Okay.
Oh, thanks, Rod. That was unexpected.
Remember the whole movies?
It's good you have the date in there, too.
Yeah, the date.
It's a wonderful spring
It is.
afternoon here in beautiful downtown Los Angeles.
Your children will see that.
Actually, I shouldn't do the talking, you should, because this thing will pick you up better than it will me.
We're at USC. 74 degrees out. It's sunny.
Thank you, thank you, thank you. I suppose there should be theme music to go along with
A
this.
theme.
This is a Bob and Rod production.
A Bob and Rob production.
And also with us
Oh.
today is Claire Weissler, our mom.
Hello.
We'll
I'm in this
rejoin.
office. We'll now rejoin.
How
All
are
the
you going to stop
participants.
having this old man in the house now all the time? Is somebody going to get
I'll
underfoot?
have to.
Get in the way?
I'll have to.
We'll rejoin this ruckus group a little bit later in the lecture room.
Yes, yes.
Bye.
gentlemen, just in case you have not seen the notice on the blackboard, I will not collect the problem sets that are due today. They are to be kept by you and studied for the purpose of getting you ready for the final examination. Now, I would like to talk to you about the connections between nuclear physics, which we have been talking about for the last 2.5 weeks, and some other very exciting field, namely the origin of the universe in which we live. And it turns out that this particular connection is much more intimately connected with the theory of nuclear particles than with anything else. I made some trivial calculations a couple of years ago by taking the total known mass of the universe. Universe, total mass, known mass. There are other unknown masses about it that we are not taking into account here. Of the order of 10 to the 80 atoms, or hydrogen atoms, as a matter of fact. If you then remember that one hydrogen atom has a mass of 1.6 times 10 to the minus 27 kilograms, you can express the total mass of the universe and calculate the density that it would have if this particular universe were to be compressed to nuclear densities. In other words, nuclear density is of the order of, I use the symbol rho, 5 times 10 to the 17, 5 times 10 to the 17 kilograms per cubic meter. Water density is of the order of 1,000 kilograms, 1,000, not 10, 1,000 to the third power, 1,000 kilograms per cubic meter. You see the enormous difference between nuclear densities and the ordinary type of densities that we experience on the surface of the Earth. If you then take the total mass of the universe, you find if it collapses to this particular density, the radius of the universe at nuclear densities is approximately 400 million kilometers. Now, please envision for a moment what we mean by this. We mean that in our own universe, there are approximately 10 to the 11 solar masses. In the universe total, there are in the neighborhood of 100 million galaxies. You multiply that by the solar masses, and you know the solar mass is of the order of magnitude of 10 to the 30th. And that gives you then an estimate of the known visible mass of the universe that you can see. Then you assume that that particular mass is going to be condensed down to what we have discussed earlier here for the fun of it, namely a black hole or a neutron star. this particular total mass of the universe is condensed down to a sphere of nuclear density, this particular density. In that particular case, this number of atoms in the universe occupies a sphere of radius 400 million miles. Now, just to give you an idea of what this 400 million miles is, it's between the radius of the orbit of Mars and Jupiter. In other words, quite small. Quite small. You have to compare that with the approximate dimensions of the universe, which is in the neighborhood of 15 billion light years. 15 billion light years. In other words, this mass, as we see it now, is contained in a sphere of diameter, of radius of 15 billion light years, where 1 light year is approximately 10 to the 13 kilometers, namely the velocity of light times the number of seconds in a year, which is roughly 3 times 10 to the 7. That gives you the number of kilometers in a light year. So we condense that particular sphere down to this rather small diameter, an orbit, a sphere between, with a radius between Mars and Jupiter. And that would be an enormous black hole, if you want. And it would contain an enormous amount of energy, because the rest energy of each of these hydrogen atoms, m0 c squared of hydrogen, of the proton, is of the order of, it's actually 938 or 39, let's call it 1,000 MeV, 1,000 million electron volts. If you multiply this by 10 to the 8, you can see what the total energy that's inside of that sphere. It turns out that the energy density, which is the total energy this here, times 10 to the 80, divided by the volume of this sphere of radius 400 million kilometers, and that energy density turns out to be 5 times 10 to the 47. In other words, you are getting really into trouble with respect to the visualization of that type of an energy. The energy density times 10 to the 47, this is electron volts, million electron volts per cubic meter. An enormous energy, an enormous energy. Now these are all rather trivial calculations. They may or may not have any relation with respect to reality at all, but it just simply shows you, if we apply the little bit that we know about nuclear physics to what we have talked about with respect to the collapse of stars, and now amplify it to the collapse of the universe, then we end up with these enormous energies, and that brings us up immediately to the question of how did our universe originally start? And what I'm doing here is I'm essentially reporting on the substance of 2 little books that I looked over carefully. One is by a physics theorist of fundamental particles by the name of Stephen Weinberg, a professor of physics at Harvard. And the other one is by 2 professors of astronomy, one at Cambridge and one at Berkeley, John Barrow and Joseph Silk. The Weinberg book is called The First 3 Minutes, and it concerns itself principally with the nuclear physics that is involved in the very early part of the universe. The 2 astronomers that I quoted, Barrow and Silk, have a book entitled The Left Hand of Creation, and it starts again, as Weinberg's book does, from the initial point of an explosive universe to what we have today. It goes all the way through the development of galaxies, planets, and life forms. So it's these two books, and if you are interested, they are written for the layman. There are no formulas anywhere in the book, except there are appendices, if you want to. And even these appendices that do contain little mathematics contain mathematics that is easily accessible to anybody in this class. So it's essentially that I am sort of extracting what I think might be of interest to you in these two books. Now, one refers to the Big Bang as the standard model of creation of the universe. But one only refers to it as the standard model since 1975. It was not always the standard model. So let me give you a little bit of a history first. The standard model was proposed by Gamow and associates. Professor Gamow, in the last 10 years of his life, was a professor of physics at the University of Colorado at Boulder. And he proposed in 1948 the first Big Bang model, namely that the universe really was created out of a highly dense discontinuity at the very start of time, t is equal to 0. And this particular Big Bang then resulted in masses flying apart, and the nuclear physics of this flying apart is going to be discussed by Stephen Weinberg in modern terms. Weinberg discusses it in the type of physics that we know since 1975. Gamow did not know a lot of the actual phenomena that are now numerically known. He proposed his theory, as I told you, originally in 1948 to 50. The Big Bang theory was not accepted immediately. As a matter of fact, it was a very undesirable theory from the point of view of most cosmologists and physicists. And so there were 3 other astrophysicists, 2 of them in England at Cambridge, and they were, let me look up their names. They were Hermann Biondi and Fred Hoyle at Cambridge, and at Cornell, Thomas Gold. And these physicists proposed a so-called steady state universe. In other words, there was not a particular discontinuity with a Big Bang from which the universe started to expand as we see it today, but it was essentially in a steady state situation. But since the steady state situation must take into account one of the most profound astronomical observations, namely the receding galaxies, what one has to do is one has to violate one of the most fundamental laws of physics, namely the law of conservation of energy, and that was taken care of by creating mass somewhere in the universe. But it takes very little mass. See, that violates conservation of energy. You have to create mass. The hand of God, if you like, creates mass. How much mass? Roughly 1 proton per cubic meter every 100 million years. Now that's not much of a violation so far as the local ideas of conservation of energy is concerned. But it is a violation nevertheless. In another way to express it, 1 proton has to be created per cubic light year every 100 years. Well, you see, 1 proton, you hardly miss it if you were to lose it, or you hardly notice it if you were to add it once per 100 years for a space volume of 1 cubic light year, where light year is 10 to the 13 kilometers on the side. So you see, it's not much of a violation, but it is nevertheless a violation. And then with that artificial device of a generation of mass, you can account for the receding masses by continuously generating new ones anywhere in the middle. Now, let me describe to you the most important astronomical observation made by Edwin Hubble in the middle 20s and published in 1929, namely the observation of redshifts observed by galaxies. And let me put a drawing on the blackboard. Where we are plotting the velocity delta V of the receding galaxies versus their distance from the observer. There are some very interesting facts about that I will talk about in just a moment. But this particular curve, well, let's not have a delta V here. Let's actually have V as the recession velocity. In other words, they move away from the observer, us on the surface of the Earth. And these observations were made with the then relatively new 100-inch telescope on top of Mount Wilson in the middle 1920s. Edwin Hubble, an astronomer in Pasadena with the Mount Wilson observatories. And if we plot here the velocities in terms of 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth, you see we are really getting up there. Well, this is high enough. And here we are plotting the distance in million light years. Million light years. As I said, a light year is the distance that light travels in 1 year and is of the order of 10 to the 13 kilometers. 10 to the 13 kilometers is the distance of 1 light year. And what we are now plotting horizontally is the distance of the galaxy for which we observe a redshift. I'll talk about the redshift in a moment. This is 50, 200, 1,000, 1,000 million, 200 million, 50 million. You see, those are the figures. 2 times 10 to the third, 2,000 million, and the last one, 5,000 million light years. These are the distances, and Hubble observed a curve that looked something like this. And he had many points because he made measurements over decades, many points for each galaxy, a particular redshift. And the redshift is simply due to the fact that the light emitted by, let us say, hydrogen, Lyman alpha, or easier to observe, the Balmer alpha line, the red line of hydrogen in the transition from n is equal to 3 to n is equal to 2 that all of you know so well. That particular line, when the source recedes, is shifted in frequency to lower frequencies and therefore to longer wavelength. Longer wavelength means a redshift. And this redshift has now been observed for a large number of galaxies. Once one has a redshift, then one is faced with another very important physical quantity, namely, how far is that particular galaxy for which we are measuring the redshift? And that's a very complicated question. One way of solving the question of the actual distance is, for instance, obtained by the so-called calibration with Cepheid variables. There are stars that blink on and off, like headlights of a car being turned on and off. And it turns out that their intensity, the Cepheid variables, have very constant intensity. So if you see some Cepheid variables in our own galaxy Close by, you can measure the distance of these Cepheid galaxies by triangulation from the Earth's orbit to the star. And you then extrapolate stars compared to the nearby one, give you an estimate of the distance of these farther away galaxies. So you can see that the distance determination of the galaxy is quite a task. At any rate, that was done, and for these various distances that are plotted horizontally here for these galaxies that I indicated by dots on this line, we observed recession velocities of the order of 10 to the 6 kilometers per second. Now, 10 to the 6 kilometers per second turns out to be a considerable fraction of the velocity of light. 10 to the 5th kilometers per second. We don't go that high. 3 times 10 to the 5th is the velocity of light. I made this curve too high. Let me cut it off. It ends somewhere here. Okay. My curve is badly drawn. But you get the idea that the faraway galaxies show recession velocities that are really becoming comparable to the velocity of light. In other words, the whole galaxy is moving with 1/3, 40% of the velocity of light away from the observer, an enormous velocity. So this is, in part, one of the most important astronomical observations. It was made in the middle 20s, published in 1929, and has been refined ever since. And one can calculate from this curve the so-called Hubble constant. And this Hubble constant gives you the change in velocity per million light years. The change in velocity per million light years, and that turns out to be 15 kilometers per second per 1 million light years distance. Now actually the first Hubble constant was 10 times larger than this because of the inaccuracy of determining distances. But this particular Hubble constant that I'm writing down here was obtained by Sandage, a well-known velocitor, astronomer with respect to modern astronomical observations, and he has recalibrated all of this in 1960. So it is a fairly up-to-date, whereas the earlier Hubble constant was obtained between 1929 and 1935. So this is a figure that can be relied on. The interesting thing is that 1 over delta V gives you the life of the universe. And the life of the universe on that particular basis turns out to be of the order of 2 times 10 to the 10 years. And 2 times 10 to the 10 years, that's 20 billion years. 20 billion years. Now it turns out that this particular figure is slightly too large. And the reason that it is too large is a complicated one. I won't go into it. It is not of any interest for the kind of survey that I want to present to you here. So the important thing now is that we observe all universes, all spiral and spherical and elliptical galaxies through the telescope to have redshifts, and the redshifts become larger the farther away these objects are from us. And that immediately brings to mind the following type of a picture. Now you are all engineers. Assume for a moment that I have a rubber balloon, and I have put on this rubber balloon dots that symbolize the various universes. Then I blow up this rubber balloon a little bit, and you look at it and you find the distance between dots is that much, 5 centimeters. Then I blow it up a little bit more, and the distance between the dots now becomes 6 centimeters. And a little bit more of the balloon doesn't burst, 7 and then 8 and then 9. You can see how when the rubber balloon expands, the distance between all dots becomes larger. It doesn't matter where you yourself are as an observer. It doesn't mean that some of the galaxies move towards you and others away. All galaxies in this particular model move away from you. Another very famous example, these are not my examples, but you find them in the literature. Another famous example is raisins in a loaf of bread. When you take bread and you have yeast in it, the cake expands. It grows bigger in volume because of the CO2 expanding the dough. And the distance between the raisins before you bake the cake is rather close, 1 to 2 centimeters apart. When the cake is fully baked, then the distance between all raisins in this dough, this is now a cake, is much increased. Every raisin is farther away in the baked cake from every other raisin in comparison to where they were before you baked this dough. So this is the model then that we have in 1929 to 35, refined in 1960, to the point that this inverse Hubble constant gives us the age of the universe. In other words, we know these things took that velocity. Calculating back means the universe started out that many years ago. 1 over the Hubble constant gives you then the time only. And we have other verifications of that time of the universe. We know, for instance, that the half-life of uranium, which we find on the surface of the Earth, is of the order of 4.5 times 10 to the 9 years. Obviously, the universe must be older than the life of uranium on the surface of the Earth. So therefore, the Earth has an age at least equal to the half-life of uranium and most likely greater. And that means that 4 times 10 to the 9 years, this is 2 times 10 to the 10. 4 times 10 to the 9 is obviously a lower boundary of the age of the universe. If the Earth lived at least 4 times 10 to the 9 years, the universe obviously lived longer because the Earth was formed later in the development of the universe. There are a number of other such age determinations that I will leave out here. Now, Einstein generated the general field equations for general relativity in 1916 and 1917. They were actually verified with respect to the deflection of sunlight in the eclipse of 1919, and the general equations of relativity, which I do not understand at all. I am an experimental physicist, but there is somebody here in this physics department, Professor Narvik, good theorist, friend of mine, who understands really how to handle this, and maybe sometime he'll give you a talk on general relativity. If you take the equations of general relativity, and Einstein did that, he could generate from his equations of general relativity a steady state universe, but he had to fudge. Nobody liked the fudge factor that he used, and he considers it one of his worst mistakes. Einstein, considers it one of his worst mistakes. There was a Russian mathematician who several years later did the same thing. He used the Einstein equations for general relativity and calculated what would happen to the universe. And he found, and this was before, ladies and gentlemen, before anything was known about the redshift and the expanding universe that we get from the Hubble observations. Before, he found that taking the Einstein equations and applying it to the universe, he obtains an expanding universe. The man was a Russian mathematician by the name of Alexander Friedman. And it's very interesting. that he had two conditions. One was the universe will expand indefinitely if the total mass contained in the universe had a certain critical or larger value. If the value of the total mass in the universe was less than the critical value, then the universe would expand to a finite size and eventually fall back upon itself by gravitational forces, so to speak, form a big bang, but he didn't say so, and oscillate out again and fall in again, except there would be friction forces, and it's not something that can go oscillating forever. But the important thing is that the Einstein equations, as applied by the Russian mathematician, did predict in 1922 an expanding universe. And the critical mass, by the way, of the universe, he gave as, and I have it somewhere here, the critical mass was 10 to the minus 30 grams per cubic centimeter. That is equal to about 3 protons per cubic meter. That's averaged over the whole universe. It's very difficult to say whether our known universe, as we see it through telescopes, and by telescopes I mean infrared, millimeter waves, centimeter waves, X-ray radiation, whether we see all the mass or whether there is a so-called unseeable mass in terms of, for instance, neutrinos. So the seeable mass, people are not quite sure how large it is. I have given you an estimate up there, but that estimate is probably by a factor of 10 too low. Okay. So we have then in 1929 the Hubble work and the expanding universe. The next big step came in 1948 by two people, as I told you, by the two Cambridge theoreticians. I always forget the name, sorry. Hermann Biondi, Fred Hoyle, and the Cornell theoretician, theoretical astrophysicist Thomas Gold, for the steady-state universe. That is to say, you generate mass anywhere inside of the universe and it flows out, and therefore you account for a steady state of the Hubble expansion by generating new mass in the middle. There is no discontinuity in the steady-state universe, but you have to violate conservation of energy by generating somewhere or another 1 proton per cubic meter every 100 million years. That was not liked very well. The other one was the theory by Gamow and associates in 1948, just about the same time, namely the Big Bang theory. The Big Bang theory received an unexpected support by a fabulous observation that was made accidentally in 1965 by two physicists at the Bell Telephone Laboratories. They were looking at the background noise by their microwave receiving antennas. Now these microwave receiving antennas that we are talking about, you think of it usually as an enormous dish. This one happened to be an enormous horn. And this particular horn could be pointed in specific directions in space. And it turned out that when they did these observations, they found a background noise, and this particular background noise was identified as microwave background radiation that required an average temperature of 2.9 Kelvin. 0 Kelvin is absolute, as you know. 2.9 is very close to 0. Now, this particular 2.9 turned out to be beautiful black body radiation. In the relative intensity of the radiation against the wavelength, and it turned out wavelength increasing this way. Let me make sure that I have the curve right. So in fact I have it wrong. the wavelength is increasing this way. Over here is 100 centimeters, 10, 1, 0.1, 0.01 equal to lambda in centimeters, the wavelength in centimeters. And the black body radiation that was observed looked something like this. And this particular curve fitted the Planck curve of black body radiation that unfortunately we haven't had much time to talk about in this particular course. But the Planck curve describes, as a function of temperature, the intensity of light at all wavelengths. And it fits perfectly for a temperature of 2.9 degrees Kelvin. One actually makes it a habit nowadays of leaving out the degree mark and just have the identification Kelvin over here. You find that many books still use a degree mark. Now, this was the second most profound observation made accidentally, namely, any electrical engineer wants to know what's the background noise in this particular circuit. These two men, and their name should be known to you. Here they are. They are Bell telephone people, Arno Penzias and Robert Wilson. And they made the observation in 1965. And they were sufficiently closely associated with the physics department at Princeton University, where there were some cosmologists and some theoretical physicists. And they immediately said, that's the background radiation left over from the Big Bang. In other words, at the time of the initial discontinuity, T is equal to 0, when an enormous explosion started. You might think of the explosion at the time when this nuclear density fireball started to expand. Now, this microwave radiation, as I said, was discovered in 1965. The curve was refined in the next 10 years. It's obviously a very difficult thing to measure the intensity of a black body at 2.9 Kelvin. When you remember that, for instance, the light bulbs that you see have a black body radiation that is equivalent to approximately 1,000 Kelvin. There's enough intensity there to be able to measure it. At 2.9 Kelvin, the intensities are extremely low. And in 1948, when Garry proposed his Big Bang, he too calculated a leftover radiation from the Big Bang of 5, he made an estimate of 5 degrees. But he never dreamt that that particular 5-degree residual black body radiation could be measured, even though it was quite within the capability, because the radar technicians at that particular time were very good. But the theoretical physicists didn't know enough about the details of radar measurements and didn't believe it was possible to make these particular measurements of black body radiation at these extremely low temperatures. Well, they were measured. They were refined from 1965 to 1975, so you got the curve actually. And the data points lie right on the Planck distribution curve. It's really quite remarkable how good this curve is known. And this particular curve, together with this particular piece of data from the expansion of the universe, together with the known ratio of hydrogen to helium in the universe, not in stars, but in the universe, that ratio is 25% helium to 75% hydrogen. These three figures have made the Big Bang theory essentially what one calls nowadays as the standard model of the origin of our universe as we know it. And what I want to do now is I want to sort of go through with you point by point. And it turns out that Weinberg, the theoretical physicist who talks about the first 3 minutes, does a very good job in giving you the details. So what we will do is we will start with him at a time that he considers he can apply nuclear theory to the black body that we have at the beginning. What's the beginning? T is equal to 0, density is too high, energy is too high. It's very difficult to make estimates. In the book he does make estimates, but here we will skip these. Let me point out why we cannot make estimates. There is a very good probability that very close to t is equal to 0, very close to the beginning of the Big Bang, that the physical laws were drastically different than what they are today. In other words, you know that the universal law of gravitation, G times mm prime over r squared, is the universal law of gravity. The Coulomb law, another constant times q prime over r squared. And then there are other physical laws of attraction, 4 of them altogether. These physical laws were different at the beginning of time and had to be approximated by what is called a universal field theory that contained within itself gravitation, Coulomb forces, the weak and the strong forces that hold nuclei together. Everything was describable at the very beginning by a single unified field theory. What's the very beginning? Theorists have come up with a time that they call the T-Planck. And that T-Planck is given by the following constants. And you see why one speaks of unified field theory. T-Planck is equal to the square root out of the universal constant of gravitation. That's the one in Newton's law of universal gravitation, G. Remember G, mm prime over r squared, that G. Times Planck's constant H. That occurs in, of course, quantum theory. That's a quantum theory H. Divided by the velocity of light to the 5th power. That's the T-Planck, and that turns out to be 1.3 times 10 to the minus 43 seconds after t is equal to 0. After t is equal to 0. In other words, t is equal to 0 is a discontinuity where the explosion begins. Nobody knows what went before. Nobody even knows what went on from t is equal to 0 to t is equal to 10 to the minus 43 seconds later. So in order to see how short this time is, I mean, these powers of 10 may mean nothing to you. The time for light to cross a nucleus. Now, how big is a nucleus? 10 to the minus 15 meters. Here comes a light beam. 300,000 kilometers per second. The time it takes for a light beam to go from one edge of the nucleus to the other is 10 to the minus 24 seconds. 10 to the minus 24 seconds is very large compared to the Planck time. You see that? By 20 orders of magnitude. This is shorter by 20 orders of magnitude. Between 10 to the minus 23 and 43 is 10 to the 20. So you have an idea of how short a time it is. At this time, it is felt by astrophysicists and nuclear theorists, particle theorists, the unified field theory describing all forces by one single unified force became effective. At 10 to the minus 33, it was beginning to show a separation between gravitation and strong nuclear forces. And later, but you see these times are extremely short, the separation between nuclear forces and electromagnetic forces. So what we will do is, we will now go along the steps that Steven Weinberg picks out and says we will consider a long time after t is equal to 0, namely 1/100th of a second. So we start 1/100th of a second after. T1 is equal to 10 to the minus 2 seconds. At this particular time, the temperature is 10 to the 11 Kelvin. Now 10 to the 11 Kelvin is of the order of 10 to the 7 eV. 10 to the 7 is of course 10 million electron volts. That's the average energy of the particles. And what particles are there? They are in thermodynamic equilibrium. All the heavier mesons that occur earlier have disappeared, and we have now only equal numbers of electrons, positrons, photons, and neutrinos. We'll leave out the neutrinos here. The densities at 10 to the 11 temperature K are of the order of the energy densities. The energy densities are of the order of 10 to the 41 electron volts per cubic centimeter. 10 to the 41. Enormous energies. And what is happening here at these particular energies, that you have a continuous exchange between the following reactions. Neutrinos will interact with protons, and the reaction is reversible to form electrons, positive electrons plus neutrons. These protons and neutrons are there in very small numbers, whereas the electrons and the neutrinos are there in very large numbers, and they are all in thermodynamic equilibrium at this particular temperature. And it is these reactions that go back and forth. Now the interesting thing is that at 10 to the minus 2 seconds, that's 1/100th of a second, 1/100th of a second. That time is very short compared to the decay time of neutrons into protons plus an electron plus a neutrino. That T is of neutrons is of the order of 11 minutes or 600 seconds. So you see the decay time of the neutrons that we found in this original soup is very long, and therefore we have equal number of protons and neutrons at that particular time. At a later time, I'm running out of time too here, at a later time of 10 to the minus 1 second, T is equal to 10 to the minus 1 second, we find that the temperature has dropped now to 3 times 10 to the 10th. Kelvin, and at that particular time there has been a small amount of decay of the neutrons, so that we have not equal number of protons and neutrons, but now we have only 38% of neutrons and 100 minus 38, which is 62% of protons, because of the decay becoming noticeable now. One can calculate this decay from the decay constants. At 1 second, at T is equal to 1 second, we have already now decreased the temperature to 10 to the 10th Kelvin. and that's 10 to the 6 eV. And in this particular case, the neutron density is of the order of 24%, and the proton density is of the order of 76%. And that changes now very little. And now one finds that at t is equal to 14 seconds, the temperatures are sufficiently low at t to, namely 3 times 10 to the 5th eV, that in this particular case, the protons, the positons and electrons annihilate. And they cannot, there are not photons anymore that will immediately split them apart as soon as they have annihilated. So they will disappear with a few of them left over, and stable nuclei form now. And as the temperature drops lower still, T is equal to, in this case turns out to be several minutes. What's the next one? 3 minutes. The temperature is of the order of 10 to the 9 Kelvin. And you find that the concentration of neutrons is 14% and 86% protons. And this particular stable concentration now gives rise to the formation of actual nuclei, because the temperatures are not high enough to split the nuclei, like for instance the splitting of nuclei that I discussed with you in the case of the deuterium dissociation, which takes 2.2 million volts of gamma rays. We don't have that energy available here anymore, and therefore the nuclei are stable. And now you have 2 neutrons in every helium nucleus, and therefore twice this gives rise to 28% in terms of weight. And that is indeed the concentration of helium atoms that one observes in the universe in comparison to hydrogen. So you can see in this very brief lecture how one utilizes what we know about nuclear physics, nuclear data, nuclear theory, how one can utilize that in order to understand the detailed processes that go on in the first 3 minutes of the origin of our universe in the Big Bang. Thank you. That will be all, ladies and gentlemen. We will see each other at the time of the final examination. Yes, I did, but I changed my mind. I'm not doing that. I don't know where I'm going. I did tell you afterwards, I changed my mind. So it would be the other day. Oh. Why did you? No. Yeah. Is there a class in this room? You're on my class. You're on the next class. Yeah. Okay.
Right.
It's too long.
Is it too long?
One more?
Robert, come down. Let me get you up.
Yeah, we gotta get that. We gotta get that.
Yeah.
Take the goddamn thing away.